All right, so today webinar is related to 3D and structural meshes. So I changed slightly the title of the presentation, but it's really the same content. I will try to give you an overview about the different workflows, as well a number of tips and tricks how to work with these 3D and structural meshes. So I have basically two examples. One is requested for several of the participants. I will try to build a 3D structure mesh without the need of a geological model, which is sometimes the case. And in the second example, we will work with some external data, so the information, the geometry is already prepared elsewhere, and we will try to mesh this or create a 3D super mesh in FEFLOW. All right, so I see Melanie, if you have any question, please write me in the chat. I will look it immediately. Okay, so the agenda of today's presentation or webinar is we will start with some announcements, a quick intro, then an overview of the different 3D meshing workflows. So what are the new workflows in the super mesh? We will have a live demonstration and at the end, enough time to answer all your questions. So the major announcements of today's webinar is our FEFLOW International User Conference, Groundwater Modeling Without Limits, which is taking place in Hamburg, Germany from the 8th to the 11th October of this year. We will finalize the program with the different presentations in the next weeks. So we have received a large number of contributions or abstracts. This will be published really soon. So if you want to take an overview about the different workshops and what is coming in the program, I would recommend you to visit our website events.thi.com/FEFLOWUSC 2024. Second announcement is, so we have a release of FEFLOW 8.1s. Last month, we have published a new update. On purpose, we didn't have any specific FEFLOW release webinar because we have this webinar, so we try to combine the whole into one. The update one has a number of different features, from CAD integration, number of options in the well manager to create groups and rules, a lot of features for geothermal applications, a new observation data dialog, which allow you to control as before the observation points, but now also budget groups and content domains, new functionalities in FEFLOW Python, and several 3D supermesh tools, some of them which I will use in the live demonstration today. This was in the release 8.1 last November. What we released almost a month ago, we have a number of enhancements related to 3D and structure meshes, basically the mesh generator. So we improve some workflows about the different ways to repair the data, but at the same time, we introduce new functionalities in the mesh generator to provide a very high level of refinement. And these functionalities will be demonstrated in today's webinar. All right, if you are new for FEFLOW, well, FEFLOW basically is a software for finite element software, which covers a number of processes from flow, contaminant transport, groundwater age, heat transfer under variable, and fully saturated conditions. Since always, our main focus at DHI has been to have FEFLOW as all-in-one solution, to have a robust software, but at the same time, a software which helps you to boost different groundwater modeling workflows. So we have a number of workflows to work through Python, to work with or interact with 3D geological softwares like we will see today, but also import-export functionalities. And at the same time, FEFLOW has a very extensive visualization capabilities. So we are leading the groundwater market in terms of visualization. And our long-term vision is to have a software which can cover the entire modeling workflow, from model conceptualization, generation of mesh, settings, simulation, calibration of the model, and also doing predictive uncertainty quantification using other tools like PES++ or PES through our FEPES programming or graphical interface. Okay, to the topic of today's webinar is related to 3D meshing. So what do we want to say when we talk about 3D meshing? So as you know, FEFLOW is a finite element software, and back into 2015 we introduced what we call 3D and structure meshes. In simple, basically, this means that we have extended our library of finite element mesh type library, which allow us to create numerical models with a high level of discretization and also acknowledge the different and complex geometrical constraints which could come from geological software, but also from geotechnical infrastructures like wells, inclined wells, or underground tunnels, pipes, mining infrastructures, mining plants, etc. So for this, to create these 3D structure meshes, there are a number of workflows. Um, Still today is the use of layer meshes is predominant in the software because it's easy to generate such a meshes. And I don't really want to say in this webinar that you should always go to these 3D and structure meshes, but if it's necessarily, you can take advantage of these technologies. So what we recommend in general, if you have simple geometries or simple geologies, you can just work with layer meshes because this is something which FEFLOW has been doing since the 70s, and we have a very robust workflow. But sometimes there are cases where you would like to simulate some complex structures. So let's imagine you have some inclined faults, or wells, or karstic networks, or pinch out of geological layers and others. So if you work with layer-based models or prismatic models, you will typically end up with unnecessarily number of elements. If you have more finite elements, there will be more nodes. And for every single node, we have resolve equation. So you are indirectly increasing the size of the problem and therefore reducing the performance of your simulation. So in those cases, you would like to resolve this internal pinching or upcropping of layers by some tetrahedrization, which can be local, but can be also in entire model domain. If you have the possibility to work with external 3D data and use it in FEFLOW, you can build a fully tetrahedral mesh. Today's presentation or webinar relates to the last point here. But okay, in any case, I would like to give you a very quick overview of all the other workflows. So the workflow number one basically means that you have elevation data, so you have point data, not surfaces. You have point data, and with this point data, you pass the data into FEFLOW, and following certain rules, the FEFLOW will construct the different slices, and the slices will define layers. After you are done with this workflow, FEFLOW will give you the possibilities to create still continuous layers, so prismatic elements, or to decide if there is an intersection. And if there is intersection, you want to decide how do you want to resolve this, so maybe with local tetrahedrization or with a full tetrahedral mesh. This workflow is through the layer configurator, can give you a number of possibilities. Now, what I show here is a simple case where we have a fault, for example, in the middle of a layer. So you can create some rules in FEFLOW to say that the slices 2 and 4 could have will define the geometry. So there is a class called fix. And if there is interpolation happening in this slice in red, then FEFLOW will know where to stop this slice in between, which will allow you to create a number of folds or such a configurations where you have a layer in between folds, or a surface is going is crossing a geological fault. So where you have a slice on the left side or on the right side, or any other case. So this workflow one gives you a number of options, and it's quite simple to use because you just need points, and using interpolation methods like invert distance, kriging, or Kima, you can achieve what you want. However, if you want to create vertical displacements of a surface, this is something that is not supported, so you will end up with some bad shaped elements in those locations. In other situations, happens that you already have a model, so like a layer-based model, or could be an structured model, and you want to take a part of this model and then maybe introduce new geological information or new geotechnical or mining information. The workflow is quite simple. With using this meshing panel that we have since a number of years, you can just select the domain or the subdomain and then tell the mesh generator, I would like to do some refinement locally, and at the same time, I can include different add-ins like polygons, segments, and points, which will be used to acknowledge which will be acknowledged during the mesh generation processes. So you can end up with cases like the one that you see here, where you have continuous prismatic layers or layer-based models with some local tetrahedrization or some unstructured meshes in locally. And in the case there is already a parameterization in FEFLOW, then FEFLOW will know how to deal with these parameters. You can decide to do interpolation from the old mesh to the new mesh. And the third workflow that we are using, or have been developing in the last years, is a workflow using the structural data. So which means this one here. So you prepare a number of files. These files will be, they have to be in 3D. So there has to be a set coordinate in the files. There is a number of file formats that we support. We build a conceptual model, or what we call 3D supermesh, and using this 3D supermesh and a number of tools that we have been implemented in the last years, you will end up defining your whole geometry. And you have a watertight domain, which will be used subsequently to create a 3D structure mesh. So what is this 3D structure mesh? Well, it's a definition of a set of surfaces. These surfaces preferentially will be triangulated surfaces. The surfaces are defined by edges. The edges are defined by points, and everything has to fit perfectly. We have access to a number of mesh generators, and we have the full capabilities to bookkeep all the information what is available in the 3D supermesh space. This will produce at the end of the meshing process a number of selections, which can be the different blocks or the regions of your geological model, nodal selections in the case of you have point ins, A selections in the case of you have polyline add-ins, and phase selections in the case of you are using surfaces to build your, or you have internal surfaces to build, for example, faults or other type of information. Here you got the overview of the different files. So on the left side, you see a number of common geological models. These geological models, they work each one differently, and they provide you at the end surface mesh, and this surface mesh is used for FEFLOW, later in FEFLOW to build our 3D super mesh. So one of them is 3D GeoModeler, which supports a Gmod file. Gmod file could contain the different triangulated surfaces or the tetrahedral mesh. If you want, you can load the tetrahedral mesh directly in FEFLOW, so you don't need to mesh it. GoCut is quite popular, and we support the set of TS files. TS is a triangulated surface, could be one or several, or you have a ML file, which is a collection of triangulated surfaces. Leak files export as his own binary file format called LFM, which contains all the set of different surfaces. If possible, I would recommend you, for the case of LeafFlow, to store the information in different pieces so you can better investigate what is happening with the meshes and see if there is a potential, the possibility to improve any of these. And might sign use DX files. Alternatively, you could use a number of generic files like shed files, AutoCAD, Autodesk, or meshing files. So in the webinar, I will show you a workflow with generic files, because in the previous demonstrations that I have been doing in the last webinars. I was working basically with geological models, and I want to show this workflow today. And why do you want to do this? Because we basically want to acknowledge all the information that is existing in the geological model, and then try to put as much as possible in the FEFLOW model. So that's an example of a 3D unstructured mesh. So this is the mesh, and that is the fully mesh with tetrahedral. So there is no really representation of layers. We are meshing and following along the different structures which come from the geological model. There is a major rule for this, and which makes quite hard sometimes to work. And this was until 2 years ago, where we were strongly depending on external data sets. These data sets, they need to fulfill a rule which is used for our tetrahedral mesh generator, in this case, TechGen. And this rule is defined as a piecewise linear complex, which in simple words, if you have a number of set of surfaces, all the surfaces has to fit together. So the surfaces needs to be connected edges, in vertices, etc. So you don't allow overlapping and crossing of these surfaces, like in the cases here on the right side. So that's a very simple example. That's another example here where you have three different layers. Unfortunately, the sport from this model create a number of bad triangulation. This is how FEFLOW see. So on your geological model, you see something quite simple. FEFLOW sees actually something very complex. And this is the input data set, what we are using for creating a tetrahedral mesh. Sometimes works, sometimes doesn't work. And what I will discuss today is a number of alternatives, how to overcome this process. So if you take this input surface triangulation as it is, what you will end up is with a representation of the geological context as you expect, but also you have a drawback that on the vertical faces, there is extremely small tetrahedrals because the original mesh is coming in that way. The original surface mesh is coming in that way. So this is something that it was in the past not possible to control, and now we are working more and more on how to improve these different data sets, because we are very aware that working with third-party software is not easy for the users, and sometimes the software, they don't offer you full control of the export of the different meshes. So the very common mistake or problem is called self-intersection, which means that you have a set of surfaces which are not fitting together. So here you have coarse triangulated surfaces, which probably come from a geological contact, and then you have a number of 5 surfaces which are very well refined, and this will come from potentially from a fault model. So they were spotted differently. The triangulation or the resolution of the surfaces does not fit, so the mesh generator per se take this, but it cannot do anything. So how do we work around the situation is what we are going to discuss. At the same time, we have been working in a number of workflows how to parameterize all the data already before the mesh exists. So you can create what we call lookup parameters table. You can connect your different regions to a quasi database, and this database can contain informations about the material name, but also hydraulic, thermal, or mass transfer properties. And when the mesh is generated, then FEFLOW will be able to populate each final element with its corresponding properties. Okay, but how do we fix all these problems? So this is what we have been working since the last approx 2 years. So we introduced a new package called FEFLOW Advanced. This is a package which requires a license. And this package is offered for subscription and professional licenses from the FH3 or FM3 up to the maximum level FNH3. What it does, this package is basically repair improper data. And when we say repair, we need to be really 100% clear what do we actually repair. So the package basically repair or identifies intersection between surfaces. And when the intersection is identified, it resolves the intersections with a new triangulation which acknowledge of the different details. The intersections could be done between surface to surface, but could be also done between surface to polyline. Why do we need to do this? Because we need to, at the end, to have a 3D super mesh, which is watertight, which does not have self-intersections, and will allow us to generate easily a 3D and structural mesh. At the same time, indirectly, you have the ability to integrate new data sets over and over every time that you require. So there are just two options, and the options are relatively simple to use. So the first one is remesh workflow and remesh basically surfaces. And if you bring a surface into FEFLOW, you can decide to improve the quality of the surface by doing a triangulation based on a given edge size. So like 250 meters, like you can see here that we have a very regular triangles, or you can also improve and say, okay, I would like to go even more finer, and it will decrease the size of the mesh. You can also do the opposite. You can come with a digital elevation model with a very fine resolution, and you can coarse the mesh if it's needed. Surfaces, so when we start implementing this workflow, we allow the user the possibility to control actually what information is relevant to keep in the surface. And for this, we use as a criteria angle. It's called sharp angle, and this angle could preserve different surfaces. So more strict you are with this preservation, so less degree of freedom you provide to the mesh, to the remesh workflow, and therefore you might not have the best quality. If you suggest a sharp angle typically of 120 degrees, then we can end up with very regular meshes. So in the string case, if you have a cube or a box, and if you remesh it with sharp, without these sharp features of sharp angle, then your borders could be also a little bit distortion by the remeshing process. But it's worth to say that this is basically not a proper surface definition. So normally you will need to have this information split. The second workflow is offer you the possibility to repair the super mesh. Repair means here we resolve the intersection. So if we have a bounding box or a domain, and if we have a plane, the repair will basically just identify this intersection, and then the outcome will be the new 3D super mesh which acknowledge the intersection and have a triangulation exactly following on coinciding both sides, the plane and the bounding box. And this is a mesh, or it's a super mesh, which is ready to be passed to the tetrahedral meshing rate. So we have been testing with a number of cases, and here I show you a few examples that are actually much more. I always very interesting to hear from you your feedback about these capabilities. So if you are succeeding or not succeeding with these workflows, so always let us know, because we are very keen to improve the algorithm. So here is a typical situation. You have a set of surfaces, then you have a domain, and then you repair. So it's basically we throw everything that is outside the bounding box, or you come with a set of surfaces here where we have a number of discretizations, and these surfaces can be basically remeshed, improved nicely, and then you can build a geological model including the faults, including the domain, remeshing, repairing, and then remeshing. Or you have such a complex set of faults. So this comes from um, data set from Germany, and the faults are intersecting in all the directions, so you can call the remesh, so you see clearly the improvement of the quality of the mesh. This surface remesh does not solve the problem of intersection, so you always need to call a remesh. And if you have a bounding box already defined, and here on purpose the box is outside, is smaller than the fault system, so the faults will be discarded. So That is the full setup. That's another data set with a bit more complex. So here, if you add the faults, then the box, then again, we intersect. From this, we can move forward, so we can improve the quality of the surface meshes and then create a final domain like this. So, but what else can we do on top of that? And this is, I put it here coming soon because it's not something that I'm going to present today. It's something that we are currently working, and hopefully it's going to come by our FEFLOW conference in Hamburg, means by the release of FEFLOW 8.2 later in November. So we are working with a number of new possibilities to help our users. And again, not all the users are working with geological software, so we want to also support this group set of users. And the workflow that we have been developing together with our partners, GOD Solutions, is the possibility to implement the implicit modeling workflow within FEFLOW. What exactly means if the user comes with a set of boreholes or points which are defined certain geological contacts. So here, for simplicity, there is only a 2D model, but this obviously this workflow is in 3D. So we have the points. So you imagine this, we solve a system of equations, so we can consider the points as a potential boundary conditions. Then the behind the scenes there is a mesh. The mesh, each member or element of the mesh get a value, what we call scalar field. And when we have this distribution of the scalar field, basically we can extract any ISO value that we require, so we can reconstruct the surfaces in the level that we want. And when we have these surfaces reconstructed, then we can create a super mesh in 3D, and therefore also a 3D unstructured mesh. So this has been tested, and I presented last 2 weeks in a conference. So this will allow us the possibility to create automatically a number of n conceptual models. So if you see here this example, we have a fault, and if we perturb the location of the different boreholes or the settings used for the implicit modeling, we can end up with multiple representations of the concept, no? And all of this has been or is currently being worked through a Python interface, so that we can easily control all of these parameters. And the result of this could end up in multiple realizations of your 3D super mesh, or therefore to 3D unstructured mesh in FEFLOW. And on top of that, but this is a more long-term vision, is if you have a collection of different conceptual models, you can also apply a number of techniques to parameterize or perturb the conductivity per each of the conceptual models. Well, okay, so with this, I would like to start with a live demonstration for today's webinar. So we are working with FEFLOW 8.1. So the latest version is update 3, which is available already from our website. Or if you have already installed FEFLOW, you can just go to FEFLOW Help About, and then there is an option to check for updates. So as I promised, I will start with example which requires only a data set that is quite simple. So we need to have the following recipe. In this recipe, we require the extension of our model domain. This is what I call bounding box. Is information again in 3D. I need to have a set of points. These points will be used to create horizons, geological horizons. Then I will introduce a fault, so it could be one or several. It really doesn't matter in the workflow. For simplicity, I will just add one fault manually, and then I would like to also introduce a tunnel, which will be represented by a line in 3D. So what is the data, or how does the data looks like, is something that I would like to show you now. And this data is, let me open it here. So I have prepared this data set, and if you're interested to test this data set on your site, just write me an email at the end of the webinar or tomorrow, and then I will share it with you. So I have just basically a set of points X, Y, Z. So here there is a different name, and no, this is really not necessarily. It's just because I use a lot of FEFLOW for even in doing interpolations. So I have just a set of points with X, Y, and Z coordinates for the horizon 1, 2, and then I also have a topographical surface X, Y, and Z. So the most, let's say, not difficult, but the requirement of this workflow is that you have a surface. How do you create a surface? You can do it in many ways. So I will show you part of the workflow which just requires a bit of FEFLOW. So you don't even need to have GIS or any other software. So what I just did here, so skipping some of the steps. So let me click. So as usual, you create a mesh in 2D. That's my 2D mesh. There are no layers, no slices, so it's only 2D. And then I have a set of points. As I was mentioning, these points consist in X, Y, Z. So do you want to create your domains for the simulation? So what I will basically do is to pass this information to, for example, nodal distribution that I create, topo interpolates, and then FEFLOW will give you this distribution here. So this will be my topographical surface. For on this, I can just with 2D, I will be able to create a bounding box for the 3D supermesh. You can just go to the layer configurator and here apply the surface that you want. Yep. Just assign the one to one. So the base of the domain will be 0. And here you are building one layer model, and this layer model will be used to put all the data inside. So how do we get this? Because FEFLOW requires an external file for the supermesh. How do we get a file from this? One workflow that not many users know is you can export all this data from selections. So if I create an elemental selection, the elemental selection can be turned to a face selection, but we are only interested in the outer faces. So this is called border face. We can store this here and say bonding box. And this bounding box can be exported in any format that you want, which is readable by the 3D supermesh. So you can export a 3D supermesh, a 3D SHD file or BTK or SMesh. So normally I will take SMesh because the original implementation of FEFLOW for the version in 7.0 strongly is basing on the TechGen, which is working with SMesh files. So we have well optimized those workflows for this mesh. So if you export it, then you will have it. So I already exported, so I'm not gonna do. And this file can be also built manually if it's simple. Otherwise, you will use FEFLOW for that. So the file contains a list of points, which contains vertices. Then below there is a block of faces, so the how the vertices are forming the faces and so on. Okay, that is one possibility to do it. So many of the FEFLOW users are also working with Python. So that's what I thought. Maybe I do a mixture between FEFLOW and Python. So I have a little script which is extremely simple. I can share it with you if you want, which requires basically PyVistas. Pandas is just to open an Excel file. And what it does, if you remember here on the on the table, we just have a set of point X, Y, and elevation. It will read a file. It will read a specific uh, worksheet from the file, and then it will pass the information as a cloud of points to PyVistas and create a surface. Then you have the surface that FEFLOW requires for the 3D supermesh. So if I run this, I'll show you, this goes very fast. Uh, or sometimes takes a second. Okay, nice. And then you can directly see here in Python the surface. So that is one of the surface, and this surface will represent one of the geological horizons. So I did this for two surfaces, so we are going to have only two geological horizons. So these files are saved in a format called STL, which is a AXI-based file format, and these are the files that are just created now. So 1738. If I look the file, that is the description of the file. So this, I'm not going to explain you the structure of the file because I will need some time, but it can be easily Googled. So you have the bounding box, you have the surfaces. Now we are able to start building a 3D super mesh. So if you go to File, New, the geometry will not be very complicated because I just want to show you the workflow. Fully unstructured 3D mesh, next. Super mesh import from Max, next. And here you load all the information that we need. So I just need to go to the right folder. And I need the bounding box and the two horizons. So it will read it. So you are very welcome here to change the different names. If your files already has some data, um, so here is, I see that my horizon is just one single polygon. So it's one polygon contained with many small triangles. But sometimes you have a subset of polygons. So you can also decide if you want to group it by any identifier. It's quite good to do it because then it will allow you to split the data. So if we have basically only one polygon with many triangles, FEFLOW cannot automatically split it unless you have done some operations to clip it. If I press finish, so I will see the bounding box with spore and the two horizons. So they are really simple. And in the middle, we will introduce a tunnel, and later we'll also cut the model with a fault. Okay, so very common, or very often you will see that I'm trying to do my box smaller than the surfaces. Why is, as I mentioned, the tool does identify the intersection. If you have a very good not overlapping, or the surface is outside the box, so it's very clear to identify the intersection. Sometimes you will try to make the surfaces really exactly inside the box, and this could be a problem depending on the precision that you're working, and especially if you're working with multiple softwares, like you do the box with FEFLOW, but the surfaces with Python, they might not exactly be 100%, and which could end up in potential errors, because if the surfaces are not touching, the technique that we have is not gonna extrapolate the surfaces and force intersection. It will identify a gap, and this gap will end up either in small tetrahedrons in between the vertical face of the bounding box and the horizons, or in the best case, it will mesh it, but you don't have regions, so you expect to see from your conceptual model 3 different layers, but since there is a tiny gap in between, FEFLOW will just recognize one single block. So that is something that you need to do. I give you a trick here. If you go to the tools, global settings, then there is the tool properties, the option called OpenGeont. You can dump this information. You can also display some login messages. If you are working with ParaView or any other software, you can also write this information in BTP or BTM files, otherwise dump it in OpenGeo file format. This we use it for basically for debugging purposes. What I would recommend you is, in any case, always use the display GeoD solutions login messages in the FEFLOW panel, because it's quite informative, so it will tell you how many blocks you have. So let's try to move forward with this. What I will do basically is just go to the super mesh processing panel. You have two options, repair and remesh. For the repair, you have the first block, and simplify repair output means it will repair, but it will do some minimal work, so it doesn't introduce additional triangle. Remesh the surfaces directly, so after it's repaired, it will retriangulate the surfaces. Generate region markers, this is what we need to identify blocks, and filter out surfaces. True means the pieces that are outside the bounding box will be eliminated. In the case of remesh, which basically means we rectangulate the surfaces, we do this process surface per surface, and we do not consider any potential connectivity in the surface. It's something that you need to be aware about this. So the vertices of the surfaces could be moved and could also create self-intersections unintentionally. So you need to be careful with this. Preserve original vertices, it will preserve exactly the shape that you have. Otherwise, it will move slightly the surface depending on this angle. And the target length, this is the size of the triangles that we will use. If you see here a 0 for all these operations, means that you are not prescribing a value, FEFLOW automatically is computed something and used for the remesh process. So let me prepare the surfaces. Let's repair, and then here in the logs I can see nicely identify 3 blocks, 5 surfaces. There are no lines, and this is a number of vertices. So that's what I mean. Is quite practical. Then do always step by step. If you go to the meshing panel, now you will see we have a generator called GOD. This is provided by GOD Solutions, so the first options are similar to what I already explained you. What is new is you can create constraints for the entire mesh. This is a global edge size constraint for all the polylines. We don't have polylines, it will not do anything, or for a set of points if you have. There are not points in, so the third option doesn't really matter. So if you create a mesh, generate a mesh, you will see that the mesh is created. FEFLOW gets the blocks, so we get all the blocks that we require, and then the different horizons here. So what we need to do next is to start introducing additional information. So for this, what I will do is I will um, basically already open a file, which will save me a little bit of time. Give me a second. Okay. So, super mesh. So let me open. So let's put the tunnel. Let's put a tunnel here. So no, I don't want to save it. So the tunnel. So that's the same mesh that you see. Surface mesh, super mesh. Inside, basically, I introduce a polyline, and this polyline is, if we look at from top, it will mimic that we have a tunnel in the domain. So what is new in the latest version or update of FEFLOW is the possibility to create refinements along different uh, blocks, different surfaces, and polylines and points. So if I generate a mesh from this, what FEFLOW is going to do here is going to create a mesh again, and then you see the middle part is more refined because inside we have some blocks which were identified. So we have the 3 blocks, and one of the blocks has a size of 100, and the other blocks, they do not have, they have a 0, so there is no constraint. And if the global size is automatically identified by 300, indirectly the block inside with 100 will be refined. So I have a block, and I have a polyline in a block refined, a polyline which is inside. I have the different horizons here set. So how do we control, how do we check the quality along this polyline? So if you have a line here, you can nicely tell FEFLOW, I would like to create a set line, and the set line will give you the possibility to create a cross section. So now here we have, this is the line. If you're not sure what is the line, so what you can do is, for example, create a selection of elements. So these are all the elements connected to the polyline. So I can go and say, okay, now I would like to go here to this and say, I would like to change the polyline by size of 50 meters. The tunnel with 50 meters generate a mesh. We can now Wait, open the 3D view. Now it's the same. If we open the polyline, the cross section, then we see a little bit of refinement, 50 meters, and you can keep trying until you find you have the refinement required. So the meshing process is relatively fast. So if we can go back and forward and control the refinement. So sometimes you don't want to create refinement at the, for example, let me put back the refinement at the of the put back the refinement of the block, let's say default, but I would like to refine the surfaces actually. So I'm set a horizon of, I could take one of the surfaces and refine this. This probably takes a little bit of extra time, but it's now ready. So now I apply the refinement at the surface level, so I can control the size of the mesh in between two blocks, inside the block at the polyline. But what if we would like to create a fold? So you can go here and use any of these tools to create a fold in the model. So I already have one created. And this tool will allow you to create a plane. You can create parallel planes if you want to create a buffer. Will basically went all the back to the initial setup, but I could also add the planes from the previous one when we already have repaired a number of things. And if you repair on that, you will be able to create surface 3D super mesh, which acknowledge the plane, the different horizons, and the channel. And to open here, because of time, to open the final model with the fold and the planes, so that now the fold has been refined. Then we have the different blocks. These blocks are created between the different surfaces. A nice possibility to check your things is to use these materials that we introduce. So I also have a little script which allow me to create some materials equal to the number of blocks that I have. So I will just run this, okay, and it's gonna create a number of blocks here as a material in the lookup table. And I can use the FEFLOW options to set material regions. I can activate this. Actually, the script could already define the different blocks or different materials for each of the selections, but I decided to do it manually to give you the possibility to see how the manual operation works. And I have all my blocks done. So I can nicely always do this to verify if the number of blocks is corresponded to the number of geological units that I supposed to get.